We will see proof of Shannon Hartley Theorem. Also the channel capacity of band limited Gaussian channel. Okay. So we will start with C. C is channel capacity, that is equal to h of y minus h of y given x max, because we know h of y minus h of y given x is the expression for the mutual information. So I max, that is equal to channel capacity. So C equal to h of y minus h of y given x max. H of y given x, that is equal to h of n. H of n is the differential entropy of the noise. That is, if x is transmitted or x has happened, then what is the amount of uncertainty related with y? So that we can take as h of n itself. H of y given x equal to double integrating f of x comma y log 1 by f of y given x dx dy, and this is equal to f of x f of y given x, that is f of x comma y. Based on the base rule, I am writing f of x into f of y given x, and we know that this double integral f of x, that is equal to 1. So what is remaining? F of y given x 1 by f of log 1 by f of y given x. This f of y given x I can write as f of y minus x. That is the integration or the differentiation that we can approximate to the subtraction. So f of y minus x, and y minus x is what? That is n. Okay, so f of n log 1 by f of n dl. Okay, that is only the remaining term. So that is equal to h of n. So h of y given x is equal to h of n. How we can write like that? Okay, so that derivation, that proof is here. We can write h of y given x equal to f of x comma y log 1 by f of y given x. Then f of x comma y, f of x into f of y given x. And f of y given x, I am writing f of y minus x here also. And y minus x is the n, that is output minus input, that will be n, isn't it? Because input plus n or input plus noise, that is equal to output. Okay, so output minus input, I will get noise, that is n. Okay, so if that y minus x I can replace by n, then this double integral f of x, that will be 1. Integral f of x, not double integral, integral f of x, because area under PDF curve will be 1. And what is remaining? Integral f of n log 1 by f of n dl. So that is equal to h of n. So now C equal to h of y minus h of n max. That h of y given x now I can write as h of n. And h of n we can write b log 2 pi e n in the terms of the b, and noise power we can write like this. Then h of y equal to b log 2 pi e s plus n. So C equal to b log 2 pi e s plus n minus b log 2 pi e n. Okay, so this 2 pi e, that will be 1. Then when I am taking b outside, inside the log base 2, s plus n divided by n. So that I can write as 1 plus s by n. So b log 1 plus s by n. So this is the proof of Shannon's Hartley theorem or Shannon's third theorem. So now we will see the capacity of a channel of infinite bandwidth. So here C equal to b log 1 plus s by n. That n can be written as n0 into b. n0 power spectral density of noise. Okay, n was the noise power, n0 is the power spectral density of noise. So n0 into b, you will get n. Okay, when n0 is multiplied with bandwidth, you will get the noise power. So b log 1 plus s by n0 into b. Then this I can write as s by n0 into n0 by s. Okay. Then the remaining b log 1 plus s by n0 into b. S by n0 into n0 by s. Then s by n0 1 by x, which means x equal to s by n0b. Okay, so I can write 1 by x log 1 plus x. Okay, then C equal to s by n0 log 1 plus x raised to 1 by x. Then we want to find the capacity of a channel of infinite bandwidth, which means b tends to infinity. when b tends to infinity, according to this equation, you know that x tends to 0. When b tends to infinity, x tends to 0. So C max equal to limit b tends to infinity c, that is equal to s by n 0 log limit x tends to 0. Okay, x tends to 0, 1 plus x raised to 1 by x. So now we can see that limit x tends to 0, 1 plus alpha x raised to 1 by x, that is tending to e raised to alpha. Okay, so here alpha is 1 itself, which means e raised to 1. Okay, so log e. So log is here, limit x tends to 0, 1 plus x raised to 1 by x, that is e. So log e equal to 1.442685. So now C max equal to this 1.422685, and what is remaining term? S by n0. So S by n0 bits per second. So this will be the capacity of a channel which is having infinite bandwidth. Okay, so here n equal to n0b, then dividing and multiplying s by n0 and n0 by s, then take x equal to s by n0 into b, then we will get like this. Then we are just applying that condition, that is b tends to infinity, then x tends to 0, and we are just dealing this term only. Okay, then we will get it as log e. So log e will be the value 1.442685, along with that s by n0. So now we will see the Shannon's limit. The Shannon's limit, for that, as we have taken n equal to n0b, here we can take s equal to eb into c. Okay, that is signal power, that is equal to transmitted energy into c. So here b log base to 1 plus ebc by n0b. Okay, and c by b is equal to log base to 1 plus eb by c by n0b. So that c by is called bandwidth efficiency. Okay, so how I can write that? EB by n0. How I will get EB by n0? Because it is the term inside the logarithm. So now I can write as 2 raised to c by b minus 1 by c by b. So now based on this, there is a plot EB by n0. That is this EB by n0. That will be along x-axis, and along y-axis r by b. That is the c, we know that always it can be approximated to r, because the maximum value of r is c. So this r by b. Okay, and here you can see that when r less than c and also r equal to c, r greater than c, what will be the characteristics for EB by n0 versus r by b. Okay, so now we will see how we will get that 1.6. Here you may notice that the Shannon's limit is 1.6. How we will get that 1.6? So for that, EB by n0, that is equal to limit b tends to infinity, EB by n0. So limit b tends to infinity, 2 raised to c by b minus 1 by c by b. That is when the infinite bandwidth, the signal to noise ratio, that is EB by n0, that approximates to this value. So here c by b equal to x, we are taking c by b equal to x. Then EB by n0 can be written as 2 raised to x minus 1 by x, and also when b tends to infinity, we know that x tends to 0. So here limit x tends to 0, 2 raised to x minus 1 by 2 raised to x. Okay. So while we are applying this L-Hospital rule, then y equal to 2 raised to x, then ln y equal to x ln 2. 1 by y dy, that is we are differentiating, then ln 2 dx. So dy by dx equal to y ln 2. Okay. Then it is equal to 2 raised to x ln 2. So here what we will do is, EB by n0, that tends to infinity, that is equal to limit x tends to 0. So we can apply d by dx 2 raised to x minus 1 by d by dx 2 here. So limit x tends to 0, 2 raised to x ln 2 divided by 1, that is 2 raised to 0 ln 2. Then EB by n0 equal to, simply because 2 raised to 0 is 1 ln 2, that is equal to 0.693. And when we are converting it to dB, we will get it as minus 1.6 dB. So that is marked in the previous graph. So now the bandwidth S by N trade-off. So for that, Shannon's third theorem we know that C equal to B log base to 1 plus S by N, then B by C log base to 1 plus S by N equal to 1, then S by N B by C. Okay, we are substituting the different value for S by N and we are finding the ratio of B by C. Okay, then that graph will be like this, that is S by N is the value in x-axis and B by C is the value in y-axis. So this is the bandwidth signal to noise ratio trade-off.